All right. Okay, so let's get phones and all that stuff just away. Okay, how would we do this? If we want to fit this line, we want to model a line to those 2 points. Fit it to a line. Yes, ma'am.
To get
Slope. Good. Let's find the slope. Very good. I don't think I'm recording it. I'll put it up as soon as I'm done. It'll be up on YouTube. I don't think you need to. So to find the slope. Yep.
y2 minus y1 over
Okay.
x2, or is it x2?
X2, oh, y2 minus y1 over x2 minus x1. Perfect. So what are the numbers there? That's right. Over. Okay, good. All right, so what does that simplify to? Devin, what's that simplify to? What's on the top? Well, you got to pay attention. You didn't know that, but you just weren't looking up here. Look up here and you'll get it. The 3's on the bottom. What's on the top? 6. 6 over 3 equals what? 2. Okay, so we got m, right? We need 2 numbers for a line. We need to be able to plug in values for m and for b, right? Line has 2 parameters associated with it. So we found m. That's good. We can plug 2 in for m, and that gives us y equals 2x plus b. Still have to find b. How can we find b? What's our strategy for that? What can we do? Find, what do you mean by that? It is the y-intercept. Okay, that's it. It is the y-intercept.
Plug in one of the coordinates.
Ah, okay, perfect. Perfect. That's it, right? Because we know that these 2 points up here, these ordered pairs, those are points that are on the line, and therefore they have to be values of x and y that work. They're solutions of the linear equation, right? They are values of x and y that satisfy the equation that make it true. So plugging them in must work. We'd probably pick the first one because they're smaller numbers, right? So if we plug these values in, I'm going to plug 1 in for x and 2 in for y. That gives me 2 equals 2 times 1 plus b. So what's b? 0. Okay, so we get the answer b equals 0. If b is 0 and m is 2, then our answer is just y equals 2x plus 0, and I wouldn't even write plus 0, right? And that's my function. Agreed? Okay? Let's extend our thinking there to our current level, dealing with quadratics. Okay, now look at this function here. What we've got, and we need to maybe review just a little bit with this, because there's a lot of different ways that we can write quadratic functions. Okay, and we've mainly, well, we've used all 3 a little bit, but now it starts to become much clearer here. We get to the end of the chapter and we're trying to fit quadratic functions, fit the graphs to the functions. In other words, we're kind of working backwards. Given the graph, or at least some points on the graph, can we come up with the function with the function that's being graphed, the function that fits this parabola? I didn't say that very clearly, but I think you know what I mean, right? So we got 3 ways we can do that. Remind me. Remind me real quick here, what are the 3 forms of a quadratic function? Okay, vertex form. Let's start with vertex form. So vertex form is always y equals what? A times the quantity okay. We'll try every letter, we'll get it right eventually. So lines require 2 numbers, m and b, to specify. Parabolas require 3. In this case, a, h, and k, right? What's a different form? And we've talked about this before.
Standard form.
Okay, we could do standard form or general form. That's y equals what?
MX.
No.
X squared plus BX plus
What are the numbers though?
A.
Ax squared plus
BX.
bx plus
C.
c. Okay, still just three numbers, right? Different meanings, but just three numbers. Okay, what about the other one? What's the other one called? You remember?
The one with the P and Q.
Well, the p and the q, right. What do we call that?
The quantity X something P and
What do we
then.
call it?
Something.
We had a couple legitimate names that worked. We could have called it, what are the p and q meant to represent?
Pi and
Not,
queso.
not vertex.
Oh my god.
Oh, is it the like either side of the vertex of the take?
Okay, yeah. What are they?
Called?
Intercepts, yeah. So it's intercepts form, right? Intercepts form, or we can call it factored form, because really all it ends up being is the quadratic function that's been factored. So this one was a times the quantity x minus what?
P
P times the quantity
X minus Q.
x minus q, where p and q are the y-intercepts. Okay, of all our choices there, which one fits this parabola the best?
The bottom one.
Bottom one? Okay, what are p and q? The intercepts, can we see what they are on this graph? Yeah, well, it's negative 6 point, you say negative 6.5, I say negative 6.431,
You're wrong.
and who knows? I mean, it doesn't, the point being that those are not convenient points for us, are they? They're not crossing at convenient places, so intercepts form is not the correct answer. That doesn't fit this one. Ah, okay, vertex form does though, doesn't it? Look, vertex form matches it because we have the coordinates of the vertex. They're convenient coordinates. It looks like the vertex is at -4, -6. Okay, that's great because we just got two of our three numbers from a single point. You see that? So if we use this form and we plug in the values, what's h? Well, okay, it's going to be x plus 4, but what is the actual value of h? -4 is the number that we're plugging in for h. The value we're plugging in for k is -6. Then if we do that, we end up with the result y equals a times the quantity x minus -4, you already told me is x plus 4, squared, plus -6 is just -6. Okay, that's pretty good, right? We got two of the three numbers taken care of. The only one we have left to find is a. Suggestions how we could do that? It is greater than 0. How do you know that? Opens up, yeah. Okay, now think back to our previous strategy with the line. What did we do with the line? We found the slope, just like we just found h and k, right?
Is it one?
It is. Okay, it is. But I want to know how in general we can. That's good. I want to know how we can find it in general. Okay, there is a little. Okay, there's kind of a trick you can do, and I'll go over that. But even sometimes that doesn't work well, and that's what you guys did. I think is you. That's really good thinking. You used kind of a. Maybe you did it right. Maybe you got lucky. We'll see. But whatever, either way, whether you knew what you were doing or you got lucky on this one, it's a trick that only works in convenient situations. But there's a method for solving this, for solving for a in that quadratic function that always works. And that's the one we can get by comparing to what we did with the line. What did we do with the line to solve for the second unknown? Oh, we plugged in a value of x and y, right? We took a solution, an ordered pair, value of x and y that we knew satisfied the equation and plugged those in. And our reasoning for that, remember, was that right now in this equation, there are 3 unknowns. I can't solve for b because if I solve for b, I'm going to get x's and y's in my answer, right? But if I plugged in 1 for x and 2 for y, then the only unknown in this equation was b, and so I can find its value, right? Can I do the same thing here? I can, because I know the coordinates of a second point, don't I? Right, look at this point down here. I've got this other point right here that has coordinates -5, -5. Now, I can't use the vertex, though. I've already used the vertex. If I plug the vertex into that, I'm not going to get anything important. Look what would happen if I did. If I plug -4 in for x, I'm going to get 0, right? -4 plus 4 is 0 squared. And on this side, I'm going to get -6. Well, I would end up just getting the answer, -6 equals -6. Duh. We know that, right? So that's not helping us. We can't use the vertex because it's already been used to find h and k. We need a different point, and there it is. But if I use this one to plug in values for x and y, I should be able to find a. So let's do that. I'll plug -5 in for y, -5 in for x, and let's see what happens. So if I do that, that gives me -5 equals a times the quantity, -5 plus 4 squared minus 6. Now all I'm trying to do here is solve for a. So let's simplify this first. I mean, let's combine these numbers. Numbers are easy to combine. We know how to add and subtract and multiply numbers. That's not a big deal. What is -5 plus 4?
Well, -1.
So I end up with -1 squared, which is what?
1 squared. Just
1, right? So I end up with -5 equals 1 times a minus 6. So what's my answer? Positive 1. Right? And so I got that was the last piece of the puzzle. If I plug in a equals 1, right there, all the parameters, a and h and k, have all been accounted for, and my final answer is just y equals 1, which I don't even write, do I? 1 times the quantity x plus 4 squared minus 6. Okay, make sense?
No. Yeah.
Okay. So there we go. All right, let's try another one. Oops. Okay, what about, well actually let's go back. We will do this one. What about that one? Do the same kind of thing, right? What are the coordinates for this top one here? That's vertex form also, isn't it? What are the coordinates of h and k? 5 and 2. Okay, so we know h, k, equals 5, 2. That helps. That gives us 2 of the 3 numbers. Now we could plug in this other one to find a, right?
Yeah.
Okay, there is a trick though. I'll show you a little trick. Is it what? No, it's not -2. No, it's, I know, I think,
Oh, it's
no, it's not 1. I'll show you a trick for finding it. Okay, here's the trick. Now, I think I kind of maybe showed you this before a little bit. If you scoot over from the vertex 1 to the right or left, looking at how much, well, I shouldn't even say 1. If you scoot over from the vertex 1 to the right or left, the amount that the function changes is the value of a, right? So in this case, if I start at the vertex and I scoot to the right by 1, I'm going up by some amount less than 1, aren't I? Everybody see that? Whatever that fraction is, that's a, okay? That's not a very convenient way to find it, though, because that's not a very convenient spot. We don't know exactly where that is. It sort of looks like 1/2, doesn't it? But we don't know for sure. Here's what we can do, though. We could scoot over some different amount than 1. in this case, what if we scoot over 2? Exactly. If we scoot over 2, that's a convenient amount because that lines up with a point vertically that's a good one, that hits right at a convenient place on the graph. So if we scoot over 2, now here's the question I have for you. How much should the graph go up if it's a quote-unquote normal parabola? If it's a parabola where a is 1, and let's take the easiest one we can think of. Let's take the parabola y equals x squared, okay? Like this one. If I go over 1, we know that I go up 1, right? What if I go over 2? How much should I go up? Should go up 4, because the function in this case is y equals x squared, right? And however much x, whatever the value of x is, y is the square of that, right? And so that's the defining characteristic of a normal parabola, is from the vertex, if I scoot over 1 to the right or left, I'm going to go up 1 if it's positive, down 1 if it's a negative, right? If I scoot over 2, I'm going to go up 4 if it's positive, down 4 if it's negative. If I scoot over 3, how much should I normally go up? That's it. 9, 3 squared, we're down 9, right? Yes. Okay, but what happened in this case? Now look at this one. When I went over 2, instead of going up 4, like I should have, I only went up 2. See what happened? So a is not 1. If a were 1, we would have gone up 4. So all we have to do then is say a times 4, right? The amount I should have gone up times whatever a actually is 2. And solve that equation. So it's 1/2, right? Because when we multiplied by a, the normal 4 that we should have gone up turned into a 2. And that's all the a does. It tells us how much we're shrinking or stretching or squashing the function, right? Does that make sense? And so that's our shortcut then. A just ends up equaling 2 over 4, which is 1/2. And I can get the answer right away then, right? I can just immediately put that into vertex form. Now, if that doesn't make sense, that's okay. You can always just plug in the coordinates of this other point into vertex form and solve for a. Okay, yes?
May I go to that?
Yes, you may. Okay. So what would this one be? Just a quick little test here. See if you can find the value of a on that one.
It's 2.
I don't think so.
Dude, they are.
Okay, we're small.
What is a there? Oh, maybe it is. Maybe it is. Actually, it's not 2. It's -2, isn't it? How did we get that? Because if I go back this way, either direction, if I go that way 2, I should go down how many? I should go to right there. Oh, that's 4.
Oh, yeah.
But it turns out I actually go 1, 2, 3, 4 more than that, so I actually go 8, right? So the equation we would solve would be 4 times a. The normal amount times a is what we got. So a is -8, right? And so a is -2. Make sense? Once again, don't have to do it that way. Don't feel like you have to. It's just a really effective way to do it if it works, if you have convenient points, and if it makes sense. But if it doesn't, just always do it this way. Just plug in the coordinates and solve for a. Okay, what about this one? Moving on. Yeah, how about that one? If you can read that. Okay, this time I didn't give you the picture. I just gave you the coordinates of 3 points. But still, we can be smart about this, and maybe we can fit this to one of our special forms, which makes it easier. Does this fit vertex form? Does that fit vertex form? No. Okay, we can actually say for sure that it doesn't this time. But even if we weren't sure, what if the 3 points were just more random? We don't know, and so can we assume it fits vertex form? No, we can't, right? So that's out of the question. We don't
Answer's
know
two.
for certain that one of those points is the vertex. Vertex form is out the window. What about intercepts form? That's the other special form. Can we see values of P and Q there?
Yeah.
We can. Yeah, what are the x-intercepts here? What are the x-intercepts?
See if you can just try it.
I know, we all have days like that. So, let's see. So, 8 and 6, how'd you get that? Okay, but how do you know those are, true, but how do you know those are x-intercepts?
X, Y.
There you go, perfect, because the y-coordinate is 0, so they have to be on the x-axis, right? Okay, that's good, good. So we get P and Q, right? Okay? Good? So we can apply a similar kind of a strategy. Now this time the vertex trip is not going to work though, is it? Because we don't even know where the vertex is. We don't have a picture. We don't have a graph. So we've just got to do that other technique. But we can plug those two things, those two parts, we can plug into our intercepts form, right? And we get 2 of the 3 numbers accounted for. So we get y equals x minus 8 times x minus q, and I still have that a though that I don't know, right? How can I find a? Go ahead.
6 instead of
Oh yeah, you're right. Yep. That's what I meant, right? I plug in the values for P and Q. How am I going to find A? Perfect, right? I've got another solution here. Look at this. There's my other solution. That's a value of x and y that has to work, so I'll plug those in. I'll plug 4 in for each of my x's, and I'll plug negative 8 in for my y. Only thing left to find is A. It's easy to do. So let's try that. So I get negative 8 equals A times 4 minus 8 times 4 minus 6. What's 4 minus 8?
-4.
Negative 4. What's 4 minus 6? Okay, negative 4 times negative 2 is 8. So it's A times 8. So 8A equals negative 8. What's A? Negative 1. Right? We got all 3 parts then. I've got A, I've got P, I've got Q. So my final answer just looks like y equals negative the quantity x minus 8 times x minus 6. Okay, now what if the question asked us to put this in factored form? Those are a little bit easier, but I'm also going to ask you to put these in general form, which wouldn't have given us any clues as to which form was the best one to start with. But you probably can see that anyway. How would I take these though? How would I put that form in standard form? Turn it from general form into standard form. That's it, exactly. All you ever do when you want to put any function into its standard form, all you're doing is simplifying. In this case, we're just going to multiply everything out, FOIL it out, distribute the negative 1, add up like terms, done. It's automatically in general form. The first example we did, what if it had asked for this answer right there to be in standard form or general form? What would I do? Yeah. FOIL out the x plus 4 times x plus 4, simplify, subtract 6, done, right? Okay, no big deal. Okay, last example.
Are you sure it's the last?
I'm sure this is the last one.
Are you sure? Are you sure?
I'm positive. Okay, so what about this one? Now, this is much harder. Well, yeah, it is. It's quite a bit harder. I want you to tell me why.
Because they're bigger numbers.
Ah, okay. Got no y-intercepts. That would have been really nice. Made it easy if I could find two of my numbers right away. And there's, what else do we not have here? So we have big numbers. We don't have, we can't use that little trick, can we? Right? Because we don't have a vertex. Right? So, not on the non-graphing calculator part of the test you can. I will show you a trick.
We can on the graphing calculator test.
I'm going to show you a great trick on the graphing calculator test. Okay? But you're going to have to be able to do this without a graphing calculator also. Well, I don't know if I'll have you do it without a graphing calculator, but there's some limitations. I don't want to say this, but there are some different strategies that apply depending on the kind of answer that you need. So in this case right here, it says write the quadratic function in general form for the parabola that passes through those points. It wants us to provide the exact coefficients A, B, and C in general form. Okay, the big problem here though is if we think about general form, ax squared plus bx plus c, none of those points give us any of those numbers directly, do they? General form, sadly, is not convenient like the other two where we can look at it and say these h and k, there they are. P and q, there they are. A, B, and C don't just pop out of the coordinates like the others did. So what do we do instead? Well, we do know that these are points that sit on the parabola. So they're values of x and y that have to work, right? So what if we take, for example, this first point, and we'll make that the blue point, how about? Okay? So the blue point, if I plug in x is 3 and y is negative 37, what am I going to get? What is this first term going to give me if I plug in x equals 3?
9A.
9a. A times 3 squared, right? So that's going to look like a 9a. What about the second term? 3b. And the last term doesn't change, right? And then the value of y, well, we're going to put the y over here. And that's just negative 37, right? So there's one equation. Unfortunately, it's got 3 unknowns in it. But we've done some of this. Hey, I want you guys to stop that, please. Okay? We've done this kind of stuff before, right? We've spent a lot of time solving linear systems earlier in the year. And we said as a general rule, if there are as many unknowns as there are, we need at least that many, unique equations, right? Different equations. So we've got to come up with, we've got 3 unknowns here. There's one equation, but we need 2 more. Where are we going to get them? Same thing with the other 2 points. Each point can give us an equation when we evaluate the function at those x's and y's, right? So what about the next one? What if we choose, this one will be green. If I plug 1 in for x, what do I get from the first term?
A.
A. Second term?
Green. No, 1B.
B. Good. Plus c equals negative 15. There's 2. What about the third one? So if I plug 2 in for x, what's the first term give me?
4A.
Plus
2B.
plus
C.
c equals, how about that? Okay, we got our 3 equations and 3 unknowns. This is now, we can solve this. In fact, this one really isn't that hard to solve. We don't even really need a graphing calculator on this one. Let's do this. I guess I'm stuck. That's right. Okay, so anyway, look what we can do here. If we wanted to solve this linear system without a graphing calculator, it's a little scary looking because it's a 3 by 3 linear system. 3 equations, 3 unknowns. But it's also a really easy one to solve because look, all the coefficients of C are 1. So here's a little trick. If I call this one equation 1, and that one equation 2, and that one equation 3, what if we did something like, let's say, equation 1 minus equation 2? Same thing as multiplying the green equation by negative 1 and adding them up. So we're using linear combination or elimination, right? What do I get? From the first
9A.
term is going to be 9a minus a. What's that?
8A.
8a. Good. So we get 8a. 3b minus b is 2b. C's cancel, right? Equals negative 37 minus negative, so plus 15.
Negative 50.
Well, hold on, but I'm adding, right? Because I'm subtracting a negative.
Negative.
So
Negative 22.
22. Negative 22. Good. Right? Okay, what if I did the same thing? How about if I subtract 3 minus 2? I'll just pick convenient ones. So 3 minus 2. 4a minus a would be 3a. Good. 2b minus b. Okay. C's cancel. C minus c. Negative 24 minus negative 15, so plus 15. Negative 9. Right? We see that? Okay. I could just, why don't I just scoot these over? I don't need all that extra space. And we could solve this one by linear combination. What if I multiply top one, I just leave alone? 8a plus 2b equals negative 22. What do I multiply the bottom one by?
2.
I could too, but probably even better. Negative 2. If I multiply by negative 2, I'm going to get negative 6a minus 2b. And if I multiply by 2, it would have been fine. I could have just subtracted. That would have been fine. Equals 18. And if I add those up, the b's cancel.
Please excuse this interruption. Just a reminder, dance team has practice today, 3 o'clock in Warburg Court.
I get
That's
2a
dancing
equals
practice,
negative 4,
3
so what's a?
Warburg Court.
Negative 2. Where do I go to find b? How about right there? Right? So 3 times negative 2 plus b equals negative 9. So that's negative 6
Negative 3.
plus b equals negative 9. Add 6. I get b equals negative 3. Good. And if I want to go back and find c, where would I go? Yeah, which would be the easiest one?
The middle one.
Middle one, yeah. So if I plug into the middle one, I'm going to get negative 2 minus 3 plus c equals negative 15. So negative 5 plus c equals negative 15. What's c?
Negative 10.
Negative 10. Well, we got it then, don't we?
Yep.
Right? That tells me that y equals a, negative 2x squared, plus b, so negative 3x, minus 10. Okay, now we could, we're about out of time, we know how to make that easier. We could have just taken this linear system here and put it in our calculators though, right? Okay? All right. Very good. Yes.